Okay, so what we've done so far is we've talked about scatter plots, and we've taken a look at the fact that a scatter plot displays the relationship between two numeric variables. We often want to use x to predict y. That's the idea, is can we find some type of predictive relationship between these two numeric variables? And we've taken a look at correlation being one way to supplement the scatter plot. It's a way to give us a numeric value that will look at strength and direction. What we're going to take a look at today is actually finding the line of best fit. And this is that term, least squares regression. What that means is line of best fit. So when you are asked to find the least squares regression, that just means find the line of best fit. So the general form of a regression equation, it looks like y hat is equal to a plus bx. A is the y-intercept, b is the slope, y hat is the predicted value of y for a given x. So the idea is we have a bunch of data that has x versus y, and we are fitting the line of best fit to it, which is this a plus bx. Y hat then is the way that we predict y based off of a given x value. Okay, so here's our first example. Carrie and Danielle wanted to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. For their experiment, they vigorously shook 40 cans of soda and randomly assigned each can to be tapped for 0 seconds, 4 seconds, 8 seconds, or 12 seconds. Then, after opening the can and cleaning up the mess, the students measured the amount of soda left in each can in milliliters. Here is the scatter plot with the least squares line on it. Okay, so we see the data, we see the line of best fit, and then this is the equation of the line of best fit. So first thing that we can do is we can predict the amount remaining for a can that had been tapped for 10 seconds. We're just substituting 10 into the equation. So we would say, really, this should be soda with a hat on it. That hat means prediction. So using our equation, we would have 248.6 plus 2.63 multiplied by that 10 seconds. Of course, you need to show that work. I will tell you that ends up being about 274.9 milliliters. That is just a prediction. If you actually tapped a can of soda for 10 seconds, it could be more than that, it could be less than that. It's very likely not going to be 274.9 exactly. That is just where 10 is on our line, but that is only a prediction. Okay, if we do another one, predict the amount remaining for a can that has been tapped for 60 seconds. Same idea, plug in 60. I will tell you, we get 406.4 milliliters. Now, how confident are you in that prediction? The 10, probably pretty confident.
This feels like the third question on the warm-up we just did.
Okay, why are we not confident in this prediction? Kiara?
It's so far away from the data that we have that the trend could change.
Okay, so far away from the data we have, that is exactly it. We don't know that the trend is still the same. So how confident? Not very confident. The trend may be different. at 60 seconds. Could be the same, but we don't know. Okay, this is an idea of extrapolation, or this is an example of extrapolation. So extrapolation is using the least squares regression line. That's what LSRL is, least squares regression line, line of best fit. So it's using your line of best fit to predict a y value for an x value far outside the domain of the x values used to create the line. So it's using your least squares regression line to predict the y value for an x value that is far outside the domain of x values used to create the line. So 60 is really far outside of 0 to 12. The data was strictly 0 to 12. What is important with this is the issue with extrapolation is we don't know if the trend continues or if this equation is still the best fit outside of the domain. Okay, interpreting slope and y-intercept. For the equation that we had, the slope is 2.63 and the y-intercept is 248.6. You are going to interpret slope and y-intercept almost exactly the same as you did in algebra. If we start with y-intercept, way back in algebra, y-intercept is the y value when x value is 0. What we have to remember, though, is that these are predictions. So you have to make sure in your interpretation you include the word predict. So if I start with the y-intercept, I'm going to say we predict 248.6 milliliters of soda will remain in a can capped for 0 seconds. So what is super important, like I said, is the word predict, and what is also very important is the units. I don't think I told you all this yet. I graded AP tests the past 2 years, and so when I tell you like these things are really important, it's because I know what students lost credit for, and that is a really small detail that students lost credit for on the past 2 tests, is not putting units when interpreting specifically slope. So we need to be careful of that. Okay, so slope, if we go to interpret that, we have to remember that slope is the change in y over the change in x. So this is really 263 over 1, or 2.63 over 1. Have to make sure we include the word predict, have to make sure we include units. So I'm going to say we predict that for every additional 1 second of tapping on the can, the amount of soda remaining will increase by 2.63 milliliters. So again, there are the units of second and milliliters. Again, we have the word predict. Of course, context. You gotta have context in every single answer. The big thing that I find here that people miss is this additional. So what a lot of times people will say is they'll say, for every 1 second you tap on the can, the amount of soda increases by 2.63. That's not the case. It's every additional second.
Good. I almost left it out because of
Easy
short
to
on
leave out.
space.
Yes.
Now I know that's important.
Okay. We okay with that? Okay. The next thing that we're supposed to do is calculate a line of best fit, but I didn't actually keep that data, so we're just gonna skip right on over that. We will learn how to do that eventually, but we're gonna next talk about a residual. We're gonna talk about a residual. We will look at how to calculate the line of best fit, and then we will take a break. Does that work for you all?
Yep.
Okay. So, what is a residual? A residual is the difference between the actual y value and the prediction for a specific x value. So it's basically a measurement of error. Our line of best fit is meant to predict y. So we want to know how far off was our prediction actually from what actually happened. The way to calculate a residual, it is the actual value subtract the prediction. Symbolically, that is y subtract y hat. Okay, way to remember this. The first way is you can just remember AP, right? AP stats, actual minus predicted. Also, this should look very similar to the formula for standard deviation or a z-score. A z-score takes the value and subtracts the mean, the specific value, and then subtracts the mean. The mean is just the prediction. So residual should look very similar. How do you interpret a residual? A residual gives the size and the direction of the error. By direction, I mean, did we overestimate or underestimate? And then by how much? Okay, questions before we actually calculate a residual? Okay. So we are going to calculate and interpret a residual for the specific can that was tapped for 4 seconds and had 265 milliliters of soda remaining. So our residual, there's no symbol, but it's y subtract y hat. This 4 seconds is the x value. This 265 is y. It's the actual amount of soda remaining. To find y hat, to find the prediction, we're going to use the least squares regression line, the line of best fit.
Which was
I'm just going to tell you what y hat ends up being when you substitute in 4. And I will tell you it ends up being 259.12 milliliters. Okay, so then we take the actual value, the 265, and we subtract that 259.12, and that gives us 5.88 milliliters. Okay, so what we should be looking at here is that is a positive residual. And we can look from our two numbers, the higher number was the actual value. So in our case, the actual value was higher than the prediction. So our prediction was too low by 5.88 milliliters. So if we go to interpret this, we would say for the can, it is this specific can. For the can tapped for 4 seconds, with 265 milliliters of soda remaining, the predicted amount of soda was less than the actual value by 5.88 milliliters. You could also say the actual value was higher by 5.88. But the idea is a positive residual rather, means your prediction was too low. I want to just answer this next question and then we will take a break. Okay. The last thing to talk about is how do we actually determine the line of best fit? So I keep saying least squares regression, and we should be asking ourselves, what the heck does that mean? What that means is if you have your data set, so I would sketch this, some type of data set. What we're going to do is we will have our line of best fit, and we will have all of these vertical errors. All of these things in red are the residuals. They are the difference between the actual value and the prediction. So all of these above the line are positive residuals. All of these below the line are negative residuals. So positive residuals, the actual value is higher than the prediction. The negative residuals, the actual value is below the prediction. So we have both positive and negative residuals. First thing for you to know is those residuals will always sum to be 0, kind of like with standard deviation. So what we do instead is we take all of those residuals and we square them like we do in standard deviation, and we sum them up. The line of best fit is where that sum is the smallest. So we adjust this line so that when we find all of these residuals and square them and sum them up, we're going to get the smallest. We're not actually going to do that, but that is what the calculator is doing on the back end. Okay, so what I want to do next is talk about, there are a few different ways that you will learn how to calculate the line of best fit. The first one is just straight up using your calculator. Do you remember how to find R on your calculator?
Yep.
Okay. So what I want you to do right now is for this data that we looked at before, the femur and humerus lengths, I would like you to find R. So put the femur lengths in list 1, put the humerus lengths in list 2, please. These are the values of A and B that I got. Do you all agree?
Yes, just give me a second.
Okay. So that is the way you find the line of best fit on your calculator. If you were going to write this out then, you would write out y hat is equal to negative 3.66, add 1.20x. You have to define x and y hat, even if they're given to you in the problem. So you would say x is femur length, put units, because we don't want to lose points or lose credit because we didn't put units, and then the humerus length, also in centimeters. Your other option is you can write it with those variables in the equation. So you might see something like this. Humerus with a hat on it equals negative 3.66, add 1.20 times the femur.
Wait, in centimeters? What are the inches? Oh, sorry.
We good? Okay, you're fine.
For y hat, wouldn't it also be good if I just kind of predicted humerus length?
Oh, yes. We have to write the word predicted. Yes, have to write the word predicted. Are you all okay that I'm just like kind of cruising through this?
Yes.
Yeah? Okay, that's the first way. That really shouldn't be anything new because you already knew how to calculate R. Fine? Okay. Here's the second way, using computer output. It is very important that you know how to use computer output. It is very unlikely on the AP test that you would get something like this question where you have to put data in your calculator. That is very rare because if you put the number in your calculator wrong, you're going to get the wrong answer and the AP test can't grade that. So what you're going to get in all likelihood is you're going to get computer output that you have to read. This is different data. This is not the same data as above. And so what you notice for this data is it gives us x, y, and a whole bunch of numbers for x and y. So the top line is a bunch of stats for x. The bottom line is a bunch of stats for y. And then we also notice Pearson correlation, that is just R. So this 0.949, that's R. And then p-value we haven't talked about, we won't talk about for a long time. Okay, so here are our formulas. Y hat is A plus BX. There are formulas to calculate A and B. A is Y bar subtract B times X bar. And B is R times SY over SX. So hopefully you can tell you're going to have to calculate B before you calculate A. So using the computer output, if we go to calculate B, the R value we get is 0.949. S of Y and S of X are just standard deviation. So here's our standard deviation column. Standard deviation of Y we can see is 5. Standard deviation of X is 1.581. So that ends up being about 3. You then have to plug that in to find A. So our A value then is going to use that 3. It's also going to use the mean though, the mean of both Y and X. So the mean of Y is 7, subtract 3 times the mean of X, which is also 3. So that gives us an A value of about -2. So then our equation is going to be y hat is equal to negative 2 add 3x, and you would say what x and y hat are. Now, I haven't told you the context of those, but if you had the context, you would put them in. So, these are formulas you need to know how to use. Have I told you yet that you do get a formula sheet on the test, the AP test?
No, but now that I know that's memorizing.
So you do.
Memorizing formulas has always been a bit of a
I have
hard
not
point.
given you the formula sheet yet, but I will.
Formula.
Okay. You will have to be able to identify where the formulas are on the sheet.
That's easier than having to remember exactly how each formula goes.
Yep. Okay. We good on this part? We got like 2 or 3 more things to talk about. Okay. The other type of computer output you have to be able to read is this type. You'll notice at the top of this type, it just straight up gives you the equation. Most of the time, you are not going to be given that. You'll be given this instead, and you have to be able to read that instead. It looks similar in that we have an x here. But the other line says constant. It's not y. So it's x and constant. So if we look at the 2 numbers next to it then, the way to read this is that negative 2 is a constant. So negative 2 is a constant. And then for this line, 3 is the coefficient on x. So if we were to write our equation, negative 2 is a constant, and 3 is our coefficient on x. Oftentimes, instead of x, the context will be written. So if this were for the femur and humerus data, instead of saying x, it would just say femur. And so then you know that negative 3 would be the slope for the femur, or would be the constant, the coefficient on the femur. So that is the other type you have to be able to read. This, you don't have to do any calculations, you just have to be able to pull the data right out. Okay. Still good? Okay. Last thing that we are going to talk about is these 2 points right here. We've talked about unusual observations before. We talked about this last class, I think. We have some unusual observations that are in the pattern and some that are out of the pattern. So for example, if our data set looks like this, and we add in a point down here that's still within the pattern, but it's far off from all the other points, what is that going to do? Do you remember?
Drag r closer to 1 or negative 1, depending
Right.
on positive or negative.
It will strengthen the correlation. So in this case, negative relationship r will get closer to negative 1. If I put a point over here instead, that is unusual because it's far off, and also it doesn't follow the pattern, what is that going to do?
Take r closer to 0.
Yes, it's going to weaken r, get R closer to 0. Okay, so the last thing to talk about with these points is this point is going to have a much different or bigger effect than an unusual point right there. So both the green point and the black point do not follow the pattern. They are both going to weaken R. But one of them is going to have a much bigger effect than the other one. A point that has a big effect is called influential. An influential point has a large effect on R, and with R, the slope of the line. Points that are influential are far off in the x direction.
In my head, I was thinking like outside the domain of
Exactly.
the main clusters.
Exactly, outside of the domain. So that black point is an influential point in all likelihood. It's probably having a large effect to weaken R. The green point is what we call an outlier. An outlier has a large residual. Yeah, it's weakening R, but not by that much. By large residual, what we mean is far off in the y direction. Now, this red point is still probably influential. So yes, it follows the pattern, but because it's so far off, it probably really strengthens R. Because it's far off and it still follows the pattern. So anything far off in the x direction, whether or not it follows the pattern, is probably influential. Anything that's still within the points but is far off in the y direction is just going to be an outlier. It's unusual, it has a small effect on R and the slope, but not a big one. Last thing that we're going to write down is how do we tell if a point is influential or an outlier? Outlier is just a visual inspection. There's no rule, you're just looking and asking, is that point far off in the y direction?
And seeing how that's so easy, there's more work involved in influential.
Yes, influential, there is not a set rule, but we need to see, does that point affect the slope and R? So what we would do is we would calculate the slope and R with the point, then without. And ask ourselves, is there a big change? Now, big change is subjective. You have to decide, do you think that it's a big change? You do not need to do that unless you are specifically asked. So real quick, looking at this example, I don't care about the context, but if it asked you, is this specific hospital an influential observation? What you would do is you would put this data in one list, this data in the other. So these are our x's, these are our y's. You would calculate R and the slope. And then what you would do is take out that hospital and calculate R and the slope again. If there's a big change, you can tell if it's influential. For the outlier, you would just have to look at a scatter plot and figure out where does that hospital fall. Okay, questions for me on what we've talked about today?